In today classes we will discuss about photometry. The branch of the branch of optics or light, in which we discuss about the light emitting capacity of a source and the illumination produced by it on a surface, is called photometry. Let's discuss some topics related to the photometry. First one is the luminous flux. First radiant flux. First we know radiant flux, represented by capital R. The total energy radiated by a source per second is called radiant flux and is usually assumed to be equal to the power consumed by the source. Its SI unit is watt. Watt is represented by capital W. Luminous flux, represented by phi. The total energy emitted by a source per second. The total light energy, here is light energy. The total light energy emitted by a source per second and represent the total brightness producing capacity of the source is called luminous flux. Its SI unit is lumen, represented by Lm. Next, luminous efficiency. Luminous efficiency represented by eta. It is defined as the ratio of the luminous flux emitted by a source to the total radiant flux, that is eta equals to luminous flux by radiant flux equals to phi by r. And it is also given by eta equals to luminous flux divided by power consumed by the source, that is luminous flux by power consumed by the source. The SI unit of luminous efficiency is lumen per watt. Next is luminous intensity, represented by L. In a given direction, it is defined as the luminous flux per unit solid angle. That is L equals to delta phi by delta omega, and it represents light energy emitted by a source per second per unit solid angle. Its SI unit is lumen per steradian and is called candela. And for an isotropic point source, omega is equal to S by R square, or 4 pi R square by R square equals to 4 pi steradian. So luminous intensity L equals to phi by omega equals to phi by 4 pi, that is phi equals to 4 pi L. Hence luminous flux equals to 4 pi into luminous intensity. Next is illuminance, represented by I. The luminous flux incident per unit area of a surface is called illuminance or intensity of illumination, and it is given by I equals to delta phi by delta S. Here delta S represent area and delta phi luminous flux. It also represents the surface density of luminous flux. Its SI unit is lumen per meter square and is called lux, represented by Lx. In case of a point at a distance r, the total normal area will be 4 pi r square. So I equals to phi by s equals to phi by 4 pi r square. That is I proportional to 1 by r square. While in the case of a line source at a distance r, as a total normal area will be 2 pi RL. Hence, I equals to phi by S equals to phi by 2 pi R into L. That is I proportional to 1 by R. In case of parallel beam of light, normal area does not change with distances. So illuminance I is independent of R. As we know that in the wave, intensity I proportional to A square, that is a square of amplitude. So for a spherical wave, A square proportional to 1 by R square, that is A proportional to 1 by R. So that psi equal to psi naught by R sine omega t minus kr. While for a cylindrical wave, A proportional to 1 by R, hence A proportional to 1 by root R, or psi equal to psi naught under root R sine omega t minus kr. In case of plane wave, as I, and hence A is independent of R, so psi equal to psi naught sine omega t minus kr. Now see the different term used in photometry in a synopsis. First is radiant flux, symbol is capital R and unit is watt. Then luminous flux, symbol is phi, unit is lumen, Lm. Then is luminous efficiency, eta equal to phi by R, lumen by watt or Lm by W. Next, luminous intensity L equal to d phi by d omega, candela CD, and illuminance I equal to d phi by ds lux. Relation between luminous intensity and illuminance, we will see this now. If luminous flux d phi is incident on area ds at an angle of incidence theta as shown as given by the definition I equal to d phi by ds, and L equals to d phi by d omega, and I equals to L d omega by ds. Again, d omega equals to ds dash by r square for isotropic point source, or equals to ds cos theta by r square. So finally we get I equals to L cos theta by r square. And from it is clear that for a given light source and point of illumination, that is L and R equal to constant, illuminance will be maximum when cos theta equal to maximum equal to 1, that is theta equal to 0 degree. That is for a given light source and surface, illuminance is maximum at normal incidence, and given by I max equals to L by R square equals to I naught. Again, for a given source and angle of incidence, that is L and theta equal to constant, we have L proportional to 1 by R square from the above equation. That is illuminance will vary inversely as the square of distance of the source from the point of illumination. This law is called inverse square law and is valid for isotropic point source only. Next, for a given source and point of illumination, L and R constant, I equals to I naught cos theta with I naught equal to L by R square. That is I proportional to cos theta if R equal to constant. That is at a given point. For a given source, illuminance varies linearly with cosine of angle of incidence. This law is called Lambert's cosine law, and according to it, with increase in angle of incidence, illuminance decreases. Now, photometry and principle of photometry. A photometer is a device used to compare the illuminance of two sources and its sources. Consider two sources of luminous intensity L1 and L2 are placed at a distance R1 and R2 from the screen so that their flux are perpendicular to the screen. The distance R1 and R2 are adjusted till I1 equal to I2. And in this situation, L1 by R1 square equals to L2 by R2 square. Hence, L1 by L2 equals to square of R1 by R2. This is called principle of photometry.